Yes, conduction and propagation of nerve impulse. Little complex area that need to learn some basics first of all. In the conduction and propagation of nerve impulse, to learn this, we need to learn some basics first of all. Then after we'll move forward towards that particular topic. That in conduction and propagation of nerve impulse, first of all, let us take about the axon here, that cyton, dendrite, and axon. Wait, wait, 1 minute. Let me adjust. Okay. So this particular area, we are looking towards in a microscope, that axon portion, that axon. Let's take the axon in clear picture. This is the axon. The cytoplasm in the axon is called axoplasm. Surrounding this particular axon, whatever the fluid present, we can term it naturally as extracellular fluid. So now in this diagram, just I am showing only axon to you. This is the axon. Cytoplasm in the axon is called axoplasm, and surrounding addition, the fluid present outside the axon is said to be as extracellular fluid, ECF. So arrangement of ions, we need to go through this particular area. In extracellular fluid, sodium ions are predominant. Why I'm saying predominant? That sodium ions present in the extracellular fluid are 10 times greater than the sodium ions of axoplasm. That means here if 10 sodium ions are present in the ECF, that will find only that one sodium ion in axoplasm. In that way, we are going to say the sodium ions are dominant over in ECF in compare with the axoplasm. And in the similar way, when it comes to the exoplasm, we'll find over the predominant one is going to be potassium ions. Okay. So need to learn this in issue wise. Actually, people will have confusion in this area when they are correlating this particular, the individual points as a combined form, then they get doubts. And many students, when they're asking doubts here, the doubts will come only that correlating the different issues in one particular point. So that's why point number one I explained. What about ionic distribution here means so many ions are present, but we are talking about the sodium and potassium because these are the major components here which are playing a major role in the conduction and propagation of nerve impulse. As I said to you, the sodium ions are more present in ECF than axoplasm. Potassium ions are 30 times greater in axoplasm. Compare with the ECF. Okay. Next, about the charge we need to discuss here. When it comes to the charge, along the length of ECF above the axial lemma, that will find the charge is going to be positive charge. The charge here positive, where that above the axial lemma, outside the axial lemma is positive. Okay, then along the length of the axoplasm in the below the axial lemma, the charge is going to be negative. The charge is going to be negative. So what I said, correlating the issue, sir. If how does this particular axoplasm get negative charge because that potassium ions are positive? So how do you say that negative charge? These kind of doubts will come for a student that if you correlate like this, the charge of the ECF because of sodium ion. If you correlate like that, definitely a doubt will come here that how does that negative charge came to the axoplasm. That's why I'm saying different issues these are. Number one, about the ionic distribution, I said sodium ions in ECF, then axoplasm. Potassium ions more in axoplasm than ECF. Okay. Next, the charge outside the axial lemma, that the red line we drawn, that is axial lemma. The charge outside the axial lemma is positive. Charge inside the axial lemma is negative. How much negative? That minus 70 millivolts in general. That the standard calculation of text is taken minus 70 millivolts is said to be resting membrane potential. Okay, standard, why I'm saying here, when you enter into the medicine, you'll find the variations in different parts of the neurons of the different parts of the body. So now that our text is taken, the standard unit of resting membrane potential as a minus 70 millivolts. Okay, so that we are talking about the resting membrane potential here. Resting membrane potential, that issues of the resting membrane potential we are talking. The charge in the ECF is because of the charge in the ECF above the axial lemma is positive. Charge in the exoplasm is negative, and in ECF, sodium ions are dominant over comparatively with the exoplasm. Then potassium ions are dominant in the exoplasm in comparison with the ECF. Okay, and during this particular condition, the charge in the axon is going to be minus 70 millivolts. This particular charge is minus 70 millivolts. So this is the condition. Okay, and what we said, there is the sodium ions are 10 times greater in ECF. The sodium ions are 10 times greater in ECF than exoplasm. Potassium ions are 30 times greater in exoplasm than ECF. That means if we say there are 10 sodium ions are present in ECF, one in exoplasm. If there are 30 potassium ions are present in the exoplasm, one in ECF, isn't it? One in ECF. So that immediately the doubt will come here when these kind of unequal ionic distribution when it present. When the ionic distribution is unequal like this, what will happen? That chemistry says till that particular ionic flow, the ions will flow in their from high concentration to low concentration, and till they become equal, the flow will continue. Okay, so let me show that particular here clearly, that we said sodium is more 10 times more and potassium is 30 times more. So simply what I am saying here, if more sodium ions are present outside, that means 10 times we'll find only one sodium ion. For every 10 sodium ions, we'll find only one sodium ion in case of exoplasm. Okay, in the similar way, potassium ions are 30 times greater when it compared with the outside. So what can be expected here? What can be expected? There may be a flow of sodium ions inside. There may be a flow of potassium ion outside till they become equal. Till they become equal, there will be a flow of sodium, and there must be. That means the chemistry says that concentration, if difference if it is present, that ions will move. Okay, but if they move, remember, if they move like that, if the sodium ions and potassium ions will become equal, if the sodium ions and potassium ions will become equal out and inside, that you can say that is paralysis, that a person can take impulses here. So means what we are saying, maintenance of concentration gradient of sodium ions more in the ECF, maintenance of concentration gradient of potassium ions more in the exoplasm is must. Okay, so that is must. So two contrasting issues I am saying here. I said that is must. Okay, very good. But it is not possible, isn't it? It is not possible that if more sodium outside and less inside. Why I am taking time here. This is a very important key concept of the topic. If more sodium outside and then inside, if more potassium is in inside than outside, definitely they'll move. So we should not allow them to move. Let us not allow them to move because we said that is dangerous. So how we stop their movement? By using ATP, by using energy. By using energy, we should not allow the sodium ions to come inside, and that we should not allow the potassium ions to go outside. Okay, this is very, very important. That means if you understand that the beauty of our body, human body, you can understand. What do you say? In muscle contraction, what that we have completed the muscle contraction, and when we say that when we are doing the muscle contraction, we require energy. In the steps, we said how we supply energy to the muscle contraction. If I ask a question, when I am not moving muscle, do I require energy? No, no need. That means when muscle is at rest, there is no requirement of the energy. That means that is the difference between the muscle contraction and nerve impulse. In case of muscle contraction, we require energy only during the action. But in case of neurons, to maintain the constant status, that means resting membrane potential require energy. Resting membrane status require energy to maintain the normal status. What is normal status in case of with respect to the axon? Having more sodium ions outside and more potassium ions inside. I said that's not possible. That's not possible because the ions definitely will move. That sodium may move inside and potassium may move outside. That is definitely not possible, isn't it? So that's why not possible. Okay, we'll make it possible by using energy. So I think you understand what I am saying. To maintain the normal condition, we require energy. To maintain the normal condition, we require energy. So with this, let us learn threshold condition also here. That means when I touch, that means if I touch the particular axon like this, if I touch, okay, let me go for the fresh page here. That we'll go to our previous page. As we said, that sodium and potassium ions and the ionic distribution we are shown here. Then what I said, we are using some energy, isn't it? To maintain sodium out and to maintain potassium in, we are using some energy. Imagine we are using some 10 number of ATPs. Just example I am talking about. The 10 ATPs I am using, not to move the sodium inside, not to move the potassium outside. Okay, so now with this we can understand what is threshold stimulus. What is threshold stimulus? The amount of stimulus energy required to conduct an impulse is called threshold stimulus. The amount of energy which is required to conduct an impulse is called as threshold stimulus that we need to go through. That amount of energy required to conduct. What is this amount of energy required? Do energy required over to conduct an impulse? Yes. When your stimulus energy is above the 10 ATPs, when I am touching, if my touching energy is more than 10 ATPs, that we say that is threshold stimulus. Got my point? What it will do, what my touch is doing, when I touch, what happens? If I am using 11 ATPs to touch particular object, a human being, so that breaks the energy which is holding the sodium out and which is holding the sodium outside, which is holding the potassium inside. That equilibrium will be disturbed over. That makes the flow of sodium ions inside and that makes the flow of potassium ions outside. That create the electric impulse. Okay, so let me show here. I'll say again, I'll go for that particular feature again. As I said to you, more sodium ions outside along the length of axis lemma in the ECF, that more potassium ions inside, more potassium ions are present inside. As I said to you, to hold them like this, I am using some energy. Okay, so to make it possible, that stimulus, my stimulus is called threshold. When it is called threshold? When it breaks this particular energy. The amount of stimulus energy required to conduct an impulse is called threshold. We define like this. But what is threshold exactly now I am saying to you? This will be helpful for you in MBBS also. This means we have huge information there in MBBS, that medical books. For that, even this is going to be the basic here. This is going to be the basic. Okay, so next what we need to learn here, influx of sodium ion. In case if sodium ion started flowing inside, influx of sodium ion, this is the very important basic to remember. Influx of sodium ion, charge increases. Influx of sodium ions, charge increases. Next, efflux of potassium ions. Efflux of potassium ions, charge decreases. By the efflux of potassium ion, charge decreases. This is the very important basic to remember. Influx of sodium ion, charge increases, and the efflux of potassium ion, charge decreases. What is the meaning of charge increase and decrease? Now let us see here. Then I'll start, all the basics are over. Now we'll start the fresh here, the resting membrane potential, the normal condition, we say resting membrane potential. That what is the voltage here, resting membrane potential, minus 70 millivolts. I'll show in the form of diagrams. If you observe, I'm not using the activation and inactivation gates here, because NCERT is not at all mentioned the activation and inactivation gates, but will include a little bit when we are moving forward, but that is not the criteria. We need to learn what is exactly happening. That means concept based learning is very important. Above the axial lemma in the ECF, the charge is going to be the positive, and below the axial lemma in the axoplasm, that charge is going to be negative. Then the predominant in case of X plus ECF is going to be sodium ions. Sodium ions are 10 times greater in ECF than axoplasm. Potassium ions are 30 times greater in axoplasm comparatively outside. So this is the issue we learn till the time. This is the normal condition, resting membrane potential here. And additionally, what I said here, to hold these particular ions and out and in normal status, to hold this particular normal status, we are using energy. That is very important. Normal status, we are using energy. To maintain the condition normal, we are using energy. Okay. So then, what then? That we need to use the stimulus. We call the stimulus energy as a threshold stimulus. Imagine, in case if I use very less energy, that means I said over to hold the particular ion outside and inside, more sodium outside and more potassium inside. If 10 ATPs are required, if I use 9 ATPs, can it conduct an impulse? No. If I use 10, no even. If I use 7 ATPs, no even. So that means here all the stimulus energies above the threshold only can conduct an impulse and make the flow of ions in and out. That we say all or none principle. What is all and what is none? What is all and what is none? Simply in our language, let's talk about this. For example, to go for a movie ticket is 150 rupees. If we give 149 rupees, does he allow the person you inside? Will he give ticket to you? No. That if you give 100 rupees, will he give ticket? If you give 75 rupees, sir, I'll watch only up to interval. Do you accept? No. So what I'm saying, what is the threshold for ticket? 150. 150. Okay. Then if I give 151, no matter. He allows. What's there inside? Above 150, you can give. That is your anxiety, your that interest we are talking about. Some people will go and black that particular when the 2,000 rupees, 3,000 rupees, they purchase the ticket. What is it exactly? That is all we are talking about. All the persons who are spending above 150 can watch the movie. Simply, I am saying that is all. What is none? If you give 149, if you give below 150, we are talking about. Below 150. Can you watch movies? No, they don't allow you to enter inside. That is none. Okay, so let us apply that here in our case. That all the stimuli above the threshold can be conducted as impulse. That means if I am using my finger to touch, if I am using the pen or needle or a sword or a bullet, whatever it may be, that is above the 10. That's why that can be conducted as impulse. That is called all. What is none? Then if I am using a small hair particle to touch, you don't feel that what it means. That is not crossed the threshold, that doesn't disturb the equilibrium. What is equilibrium in the case? More sodium outside, more potassium inside. That is called equilibrium. That to break the equilibrium, we need some energy I'm talking here, because to maintain the equilibrium, we are using energy. Okay, so to understand well, I'm saying this example, not like that. Here you'll find a particular vein, internal artery, internal carotid artery, we use it to say little deeper it is. You may know that arteries are deeper. If we hold that particular internal carotid artery for 30 seconds, what happens? You can't supply the energy to maintain ions. That means here brain is present. If present, here only it's present, isn't it? that 100 millions of neurons will have 100 billions of neurons. So every neuron requires some energy. If I say for what, now we can answer for what. To maintain more sodium outside and more potassium inside, they require energy always. Always, if you think, if you use the brain or not, no matter, you require energy. That because to maintain like this. Okay. If I don't supply oxygen and nutrients with the help of blood pressure, if I press here, you can't press no matter here. That is trained people can do that. So that what I'm saying, if that the 30 seconds of period of time, if I can't supply energy, almost paralyzed state it will come. Or else for 1 or 2 minutes, if you don't supply, that what happens? All the sodium out and in equal, all the potassium out and in equal. We call that status is coma. That's why the doctors used to say, even if I supply energy, that may not get back again. So how can we say that the damage is over? So that means the maintenance of more sodium ions outside, maintenance of more potassium ions inside is a crucial point. To say that only, I just yes, this much number of examples here. Okay, that only. Even that also threshold and all are non-principal also in that angle I am saying, I am explaining that particular issue. Okay, is it clear now? Now let's move. Let's move here. Threshold and all or none also will end. That's over. It's now onwards very simple. It is going to be. What is threshold? The amount of stimulus energy. The amount of stimulus energy above the threshold. What is threshold? The amount of stimulus energy required to conduct an impulse is called threshold. What is all or none principle? The amount of all the stimulus energies above the threshold can be conducted as impulse. All the stimulus energies below the threshold cannot be conducted as impulse. That we need to understand. Okay. Next, let us see what happens when this particular at this particular time, just by what I am saying here, the sodium inactivation gates are open and sodium activation gates are closed, potassium gates are closed. Then when I start giving stimulus, what happens? Here, I'm not a good artist here, just I am putting, I have to say, I think so, isn't it? My finger it is, my finger. I'm touching that area with energy. So, when I started giving stimulation here, when I start giving stimulation, let us see what happens. That breaks the threshold stimulus energy and that makes the opening of sodium ions. That sodium ions will start moving inside. The sodium ions start moving inside. For that, the voltage, because of the movement of sodium ions at minus 72, it reaches to minus 55. That means plus 15 millivolts it was increased. That is the stimulation for the opening of sodium activation gates, and more sodium ions started coming inside. More sodium ions started coming inside, and because of that, charge will increase up to plus 45. What do you say this as? Depolarization. When you say resting membrane potential as polarization condition, now we say this condition as depolarization. What is the action membrane potential? The charge, the action membrane potential is plus 45. Okay, the action membrane potential is plus 45. Okay, so minus 70 to minus 55 because of my threshold stimulus. Then after that, the sodium activation gates are open. That brings the charge increases from, as I said to you, remember that influx of sodium ion charge increases. Now it is increased, reached to plus 45 action membrane potential. This action membrane potential need to move forward, isn't it? Now here it is plus 45. Then along the length, what can be expected? Minus 70 along the length of axle MR. There I gave stimulation. That's why it reached to minus 70 to plus 45. Okay, so what next? What next? This plus 45 should come here, should change this area for minus 55. That brings the influx of sodium ions here also. Okay, and that makes the opening of sodium activation gates, and that brings plus 45 here also. Okay, okay, my work is over. I am I transferred this particular charge to the next one. What about this area? This area should come back or not? This area need to come back. What do you call this particular feature as? repolarization. Now the charge need to decrease to get normal position. After passing the voltage moving forward, we need to bring this particular charge that to the normal condition again. For that, I am using potassium voltage gated channels during repolarization. Potassium voltage gated channels. Okay. So simply what I am saying, influx of sodium, charge increases and increase. Now I want to decrease the charge. So charge need to be decreased. For that, what I am using? Potassium ion. So that for that potassium voltage gated channels are open, the potassium ions are started moving outside. Okay, that brings in this particular area the normal condition. What do you call the normal condition as? Again, minus 70. That is said to be repolarization. That is called as repolarization. But here even they don't stop. Potassium still moving forward, and the leads to the more decrease of particular charge here, minus 90. That minus 70 is the normal condition, isn't it? Minus 70, but less than minus 70 it was reached. That's why we use it to say this as hyperpolarization. This condition as hyperpolarization. I have some problems already. Okay, so this is called hyperpolarization. This condition is said to be hyperpolarization. Minus 90. Why minus 90? Why minus 90? Why don't they stop at minus 70? Imagine if they stopped at minus 70, what can be expected? This plus 45 may come back or may move forward. There are two possibilities it will become. So that's why we can say that staying the minus 90. Okay, so imagine this person is taking rest on the chair, and this person is sleeping on the bed. Hyperpolarization, that means rest. Hyper rest we are talking. Okay, what this person is doing, standing. Depolarization we can see. So which one is easy here? This is easy. So this particular plus 45 will make this person to stand. Can you make the person who sleep immediately at stand? No. So just I am giving example here. Okay, so that what do you say? Hyperpolarization. Always the point before the depolarization is going to be hyperpolarized in state. We don't have aims at present. If we have that assertion, reason question will come like this. Always the status before the depolarization is going to be hyperpolarized. Why? Why? To make always the conduction of impulse in forward condition in one direction. Okay, so that is the importance of hyperpolarization. When you pass this particular here, when it becomes plus 45, okay, all became mess. Let me let me hear that. Okay, we'll take new paper. So now this is the condition, minus 90 plus 45 minus 70 minus 70. This is the condition. Okay. So then when it makes this particular area to move forward and this area reached to plus 45. So what can be expected in this particular area then? Minus 90, isn't it? So now my work is over. Now I can get normal here. Now I'll become normal in this area. The point of generated area become normal. So then it starts again the story. Plus 45 should move forward. Okay. Not to get this particular backward, not to move this particular backward. What we have to do? We need to do that plus 45 before depolarization. It should be hyperpolarized state. Okay. So I'm showing everything in one place. Hyperpolarization, and this is said to be depolarized condition, and this is a resting condition or polarized condition we can see. So this is a condition. It's just a journey from minus 70 to minus 55, which is brought out by threshold and by the influx of sodium ions, that plus 45, the depolarization we can say. After that we are getting back to normal again, minus 70, that is called repolarization. To prevent the action potential not to come back, I am going back to the minus 90 hyperpolarization, then reaching back to the normal position. That means when I touch like this, that area will change like this, minus 72, minus 55, plus 45, minus 90, minus 70. Is it clear? And when these kind of explanation will happen, definitely a doubt will come. Clear explanation it is. I know this. This is very clear explanation. I say influx of sodium ion increases the charge. Okay. So that means after the completion of the story, now where is the sodium ion? It is inside. And I said efflux of potassium ion. This is inside. I am using this inside outside language because we have the text language is like this. Okay, next, after these particular actions, after whatever I explained here, influx of sodium ion charge increases, efflux of potassium ion charge decreases. When I said like this, that immediately doubt will come here. Immediately doubt will come. This is not normal status, isn't it? So that's why by using some energy, you have to bring this sodium again to their normal position. What is the normal position? That in the presence in the ECF. And you should bring potassium again to their particular normal position. This should occur parallelly when these events are happening. That means repolarization and depolarization, hyperpolarization. We are learning this slowly actually, but this will occur in the fraction of milliseconds. Okay, for that, what we use? Sodium, potassium, ATP pump, or simply we say, we use energy to maintain their original positions back again. Then after, they'll get ready, like the situation what we said in the first day, like sodium ions are more in outside, potassium ions are more in inside. So this is the condition. We can say this condition is normal condition. But here, to increase the charge, we used sodium. To decrease the charge, we used potassium. They changed their respective places. Then after that, we need to use energy again. Energy again to bring that particular sodium out from inside, potassium in from outside by using energy that we call sodium potassium ATP pump. Then only it will be ready for to take an impulse. It will get ready to take an impulse here. So we can feel this. If I touch like this, in the fraction of milliseconds, again and again, I'm giving stimulus, it is taking. What it means? That the issue I'm explaining from last 35 minutes will happen in the fraction of milliseconds. In the fraction of milliseconds. We continue the class with the synaptic transmission also. But before that, let us watch a video here. Let us watch a video about this conduction and propagation of nerve impulse. Then when it cut down, you please log in immediately. No need to take a break. Immediately log in. Along with the synaptic transmission, we'll complete that area today. Okay. So now I am showing a video to you about conduction and propagation of nerve impulse. We'll watch a video. Let me go to that particular area. Nerve impulse. Okay.
A nerve impulse is an electrical current that travels along dendrites or axons due to ions moving through voltage-gated channels in the neuron's plasma membrane. Voltage-gated channels open and close in response to an electrical voltage, so they are affected by changes in electrical charge around them. When a neuron is at rest, a charge difference is maintained between the inside and outside of the cell. This charge difference is produced and maintained largely by active transport using sodium-potassium pumps. The pumps send sodium ions out of the cell and bring potassium ions in. While other channels allow some flow of potassium ions back out of the cell, the sodium ions cannot easily get back in to replace the lost positive charges. The overall result is that the exterior of the cell has a net positive charge and the interior has a net negative charge. The difference in charge between the interior and exterior of the cell is called the resting membrane potential. A nerve impulse begins when a stimulus disturbs the plasma membrane on a dendrite, causing sodium channels to open. Sodium ions flow into the cell, lessening the charge difference at that location. If the change is enough, it will cause nearby voltage-gated sodium channels to open. This allows so many sodium ions to flood into the cell at that location that the membrane there is depolarized, with the local region inside the cell having a net positive charge and the outside of the cell having a net negative charge. This affects neighboring voltage-gated sodium channels, which then open, moving the depolarization along the membrane. This moving depolarization is called an action potential. Changes occur behind the action potential to restore the resting membrane potential. The voltage-gated sodium channels close and voltage-gated potassium channels open. This allows a rapid flow of potassium ions out of the cell, repolarizing the membrane so that the inside is again negative and the outside positive. This is followed by use of sodium-potassium pumps to fully restore the resting membrane potential and to reestablish proper concentrations of sodium and potassium ions inside and outside the cell.
Okay, so the simply what we need to remember in this particular case, influx of sodium ions is going to increase the charge, and efflux of potassium ions is going to decrease the charge. Influx of sodium ions increase the charge, and efflux of potassium ion decrease the charge. Okay, so during these particular conditions, an increase and decrease in the charge, the sodium reached inside, potassium reached outside during this particular action membrane potential condition. So getting into the normal means by using sodium potassium ATP pump, potassium ATP pump, we are actually, by using sodium potassium ATP pump, we are sending that particular sodium back again to outside and potassium back again inside. Okay, so we'll read that statements also when we go to the PowerPoint presentation of this particular area. But to understand anything, one thing you need to remember that sodium normal condition is present outside. Outside means ECM. Potassium normal condition is inside. That means in exoplasm. Then only you can understand sodium potassium ATP pump also. Okay. So let me continue here the synaptic transmission. Just log in immediately. That I'm going to stop this. Log in immediately to continue the synaptic transmission here. Okay.